That's nearly caught.
Great. Should I introduce Soledad? Awesome. Okay, so Dr. Soledad Villar is an assistant professor in the Department of Applied Mathematics and Statistics and the Mathematical Institute for Data Science at Johns Hopkins University. Prior to joining Johns Hopkins, Soledad was a Moore Sloan Research Fellow at the Center for Data Science and Courant Institute at NYU, a collaboration scientist with the Simons Foundation, a research fellow at the Simons Institute, and before that was granted her PhD in mathematics from University of Texas at Austin. Soledad works in a variety of interesting areas, broadly studying computational methods for extracting information from data. Today, we're fortunate to hear from her on the topic of equivariant machine learning from invariant functions. Take it away, Soledad.
Thank you, and thank you all for the invitation. And yeah, I'm very happy to see you all. So please ask questions if you have questions and comments or anything. So I'm going to talk about equivariant machine learning that has to do with machine learning that obeys symmetries. And I'm going to explain some work that I'm doing right now where we are using classical invariant theory to parameterize equivariant functions and then using that for machine learning. So in this slide, I try to justify why we care about symmetries in deep learning. This is just a simple, like, I don't know, some justification for this. So you know that get many solutions when you have more parameters than data, and you typically do, is they need to obey certain structure. So there's like a choice of architecture is very important for the success of these models. So in particular, the convolution neural networks are very successful at doing image processing, and recurrent neural networks and now transformers are successful at identifying processing text data. And of course, when you're working on graphs, you use graph neural networks that implement some form of message passing. And all of them have incorporated the symmetric structure of the data or of the problem in the definition of the architecture in an implicit or explicit way. So for instance, graph neural networks learn functions on graphs. And so if you have a graph like this, you can express it as an adjacency matrix. The representation of the graph as an adjacency matrix is not unique. There's some redundancies, which is like if you write it as a matrix, you permute rows and columns, and you get another matrix that represents the same graph. So if you're going to learn functions on graphs as a function of the matrix, then you want to factor out all these symmetries and redundancies. And graph neural networks have that property. So they're functions that obey the symmetries of this problem. That is very related to some other symmetries that show up in other circumstances. I'm going to discuss that later. But before, I'm going to say what is invariance and equivariance. So the definition is the following. So you start with a group G that acts on a data set, and you say that a function is invariant if when you act on the input, the output doesn't change. That's it. So for instance, this is an image classification. If I rotate the image, the classifier, shouldn't change their output. So if you also have an action in the output, then you say that the function is equivariant if every time that you act in the input, you must act in the output by the same group element. That doesn't mean that the action in both spaces need to be the same action. It's just like you have an action, but by the same group. So for instance, here I have a particle simulation, and when I apply a rotation to the input, then the output rotates in the same way. Someone asked, what symmetries appear in 1D convolutions versus 2D convolutions? So, okay, yeah, that's an interesting question. So the symmetries of the convolutions are just translation symmetries. Like if you have an image and you apply a convolution to an image with a fixed filter, then that function is translation equivariant. So if you think about like the image say in the torus, so that you can, yeah, you have like that, then the convolutions are translation equivariant. If you want it to be rotation equivariant, or if you want to add more symmetries to the functions, then you will need to design the filters in a specific way so that they satisfy those symmetries. Does that answer your question? So yeah, so convolutions. This is equivariance, and so basically equivariant machine learning finds a way to parameterize the class of functions that are equivariant with respect to a group action, or invariant with respect to a group action. So then once that you parameterize the class of functions and every function in that class satisfies the symmetries that you want, then you solve the learning problem by solving an optimization problem in this class of functions. That's the idea. And this has many applications. So for instance, we can work on images, or like images that come from scientific domains. So for instance, with images, I talk about some more general, for instance, dynamical systems like fluid dynamics that you can express in some form of like geometric image, where like each pixel has maybe a vector or a tensor. And maybe you have that these simulations are generated by some fluid dynamics, and the fluid dynamics obey certain symmetries. Maybe graphs, I already mentioned, also have some symmetries. And then if you have like some particle systems, like the solar system, or particle physics, or protein folding, in all of these problems, you can describe them in some way that needs to obey some symmetries. And this is an intrinsic thing in physics problems. And I took this quote from this book over here. It's like very heavy book called Modern Classical Physics, where by Thorne and Blanford, that says that the laws of physics must be expressible as geometric, coordinate independent, and reference frame independent objects. And these are relationships between geometric objects like scalars, vectors, and tensors that represent the physical entities. So that says that when you express the physics, then you need to have this like form of expressing the physical problem that is independent of your choice of coordinates, of your choice of units, etc. And those choices make a redundancy in the problem that requires you to have symmetries. And so if you're going to do machine learning for physical problems or for the physical science, you need to be able to factor out the redundancies of the representation of your problem, so then you are able to generalize to domains or problems that you haven't seen before. Like that, my argument is that this is the correct way to do it. And so, so what am I saying here? Why am I doing this? Because equivariance and invariances provide the correct inductive bias. This is what Thorne and Blanford argue in their book. This is actually the first paragraph of the first page of the book. And this is also something that will allow you to improve your learning, because you're going to have better sample complexity, it's more generalization error. This gives you the right model for your learning. And this is also a source of interesting mathematical questions, such as, for instance, how do you learn these invariances from the data? How do you learn what the symmetries of the problem are from the data? How do you design the algorithms that exploit these invariances and equivariances? And how do you quantify how much do you gain by imposing these invariances and equivariances? There's a question. No questions. Great. So far, so good. And so another, well, I just mentioned why symmetries are very important in physics. And I should mention that there is a very large area of research that is called physics-informed machine learning that basically incorporate physical principles into the design of machine learning models. And in this talk, I'm gonna give a few examples, and I'm gonna tell you how we can use invariant theory for specific problems coming from physics and in general. And so maybe something interesting to mention is that Noether's theorem tells you that every differentiable symmetry that is generated by local actions corresponds to a conservation law. So for instance, if you have a dynamical system that has a space translation symmetry that is in correspondence with the conservation of momentum, or if it has like a rotation or reflection symmetry, then that corresponds to the conservation of angular momentum. And if it has a time translation symmetry, so say I observe this dynamical system now, and I predict 10 minutes from it, and then I do that next year from the same initial position, then the prediction shouldn't change. That kind of time translation symmetry, this corresponds with the conservation of energy. So symmetries correspond to conservation laws in some particular cases that have to do with physical systems. Not all symmetries correspond to conservation laws. Yeah. But that's it. So the groups that I'm going to focus on today are the orthogonal group, the group of distance preserving transformations of Euclidean space. So basically if you can represent them as matrices, as like the matrices R, so that R transpose is equal to the identity, or we can just focus on the rotations, which are the orthogonal transformations that preserve orientation. So basically the ones that have determinant 1. Also, the Lorentz group is a very a different bilinear form, which is not positive definite and makes the things a little bit more complicated, but has similar properties. And then, of course, permutations. The permutations act on the graphs that I told you before by permuting rows and columns of the adjacency matrix, and also act on sets by just permuting objects. So here, I guess this is an example of a group acting in different spaces in different ways. So, okay. So the next question is, okay, we know I convinced you so far that we want to implement the symmetries in the machine learning models that we're going to use. And the next question is, how do we do this? So basically, how do we restrict the class of functions where we perform the learning so that every choice of parameters delivers a function that is invariant or equivariant with respect to a group action? Okay, so we can do it in like a weak way, which is like not really enforcing it, but kind of promoting it, which is data augmentation. Data augmentation is something that is very widely used and also studied in machine learning. So basically, what you can do is like, if you know that if f of x is equal to y, then f of gx needs to be equal to g times y, then you can take your training set and then apply the group elements to your training set and add that and their corresponding group element applied to their labels to the training. So now you have a larger training set and you use that for the training. And then you hope that you take x, y, and you augment to gx, gy. And I don't know, you take the union over G if you want of these things. And then this is your new training set. You hope that implements the symmetries in some way. Another way but this actually doesn't really give you the guarantee that the function that you obtain is going to satisfy the symmetries. But you may expect that it may satisfy the symmetries or something very close on the training data at least. So, and maybe you can analyze, and there's some analysis, there's some paper by Lee Dobryvan, and I think Edgar Dobryvan gave a talk here last year where they do that. Then the other thing that we can do is to incorporate the symmetries using the fact that the symmetries correspond to conserved quantities sometimes. So you can incorporate a penalization for these quantities not being conserved and hope that that enforces the symmetries in some way. So these, I guess, these two methods do not really implement the symmetries, but promote the symmetries. And then the other way that you can do it is by this architectural design, which is what I just told you, which is to restrict the class of functions to actually all the functions that satisfy the symmetries exactly. And sometimes you can have a guarantee that every function in your hypothesis space that your hypothesis space can approximate every function that is invariant or equivariant. That's not always the case, but in some cases you can do it. And so the way people do this is using the idea of weight sharing, which is basically message passing, and equivariant convolutions, where like you do convolutions with filters that are symmetric, and so they share some weights. And there's also the idea of using irreducible representations to use symmetries as constraints and invariant theory. So I can explain all these three. Maybe I'll start with the first one and the last one and see if I have time for the middle one. But basically, I'm just going to explain how you do this algorithmically. So the first idea is the one based on irreducible representations. So the idea comes from extending the notion of the classical feed-forward neural network to equivariant functions. So basically, feed-forward neural networks are the things that you classically see with this kind of drawing, which is basically you have your input, you apply a linear layer, then you apply a non-linear pointwise activation function, then you have another linear layer, etc. So it's like a fully connected feed-forward neural network. So this is your input, then you have a linear layer, then you apply a non-linearity, then another linear layer, etc. So if you want this function f that you express of this form to be an equivariant neural network, something that you can do is you can replace these linear layers by linear invariant or equivariant layers, depending on what you're looking for. So say equivariant. So what does equivariant mean? It means that when I apply the linear layer to the group element applied to the input, then you get the group element applied to the linear layer applied to the input. Basically, that's it. Just this diagram commutes. So the issue that this has is that there are not that many linear equivariant or invariant functions. So for instance, think about, like, say that you have a function that takes a vector and outputs a vector and is equivariant with respect to rotations. So if I rotate the input, then the output has to rotate. So if that's the case, the only linear equivariant function that that is equivariant with respect to rotations is actually just like the identity, a multiple of the identity. So then that tells you that actually, if you do the restriction of the linear layers to be linear invariant or equivariant, then you may lose a lot, and then you may have a class of functions that is not really expressive, that can only express very small things. So that's a problem. And then the other problem is that how do you design these activation functions so that you don't lose the equivariance? So that is compatible with the group action. So in the case of permutations, that's very easy, because if I apply, like if my group is permutations, then I can apply any function pointwise. As long as I apply the same function to everything, then you don't have issues. But if your group action is different, then you may encounter some issues at finding which are the correct pointwise activation functions that you can use. So I can tell you how people solve this issue number one. And the way they solve it And then I must say there are two papers, one by Condor and one by Maron, that kind of like started these ideas, but there are many more now. So basically the idea is to extend the action to tensors. So the idea is that I want to define a function that goes from RD to RD and is equivariant and is linear. So now what I'm going to do is, instead of just working with an RD, I'm going to work with the tensor product of RD with itself. And the output is going to be a tensor product of RD with itself, maybe of different order. And I'm going to just find all the linear equivariant functions that go from here to here. And in order to do that, I need to extend the action of the group to tensors. And the way it's extended is by the way that you would expect, which is like if I apply the group element to this tensor, then the group elements, the action is applying the group element to each of the components and then tensor that out, which is what I wrote here. So now the question is how to parameterize the linear equivariant functions on these tensor objects. Does that make sense? So in order to do that, basically the idea is to use group representations. So basically a group representation, you can see it as an action of the group in the space of linear functions of a vector space to itself, which are invertible. This maybe you have seen it before, maybe you haven't, but basically the idea is that when you write a representation of the group, then this allows you to represent the group elements as matrices, and the group multiplication would be the same as the matrix multiplication. So that's a way to think about group representations. It's just a way to express your group elements as matrices, and then the multiplication in the group corresponds to the matrix multiplication. So if, for instance, if you have a permutation, then you can represent it as a permutation matrix, and then the composition of the permutation corresponds to the multiplication of these matrices. I don't know if I have the example here. No, but yeah, if you have any question, we can go into it. And there's the notion of irreducible representations, which is the idea that, okay, if you have a representation which is a group action of the group into the space of invertible functions from V to V, invertible linear functions from V to V, then what you can do is you can ask whether there exists a subspace of this V, so that when you apply this group action on this subspace, you continue, the output is still in the subspace. That would be a sub-representation. And so the ones that are irreducible are the ones that the only sub-representations are kind of like themselves or zero. So it's kind of like a notion of, yeah, like irreducible object. So once that you have your representation, you can decompose it in these irreducible objects. And the key result is called Shor's lemma, that tells you that a map between two spaces is equivariant if and only if it sends sub-representations of the subspace into sub-representations of this subspace. And in order to have sub-representations of a map between an irreducible representation here to an irreducible representation here, these irreducible representations need to match. So the dimension need to match. So basically the Shor's lemma says that if you have an irreducible representation in V, an irreducible representation in W, and you have a map that sends V to W, and this map is equivariant, then these two vector spaces need to be isomorphic. assuming that the representation is irreducible, right? And so, so sometimes you can, you can see equivariance with this commuting diagram, maybe. So say you have B, a vector space, W is a vector space, and then you have the group action that sends V to V, the group action that sends W to the W. So so then the function is equivariant if applying the function and then the group action is the same as applying the group action and then the function, right? Because it's like f of rho b of g times b is equal to rho w of g times f of b. So this is applying the group action and then the function, and then this is applying the function and then the group action. That's it. So the short lemma tells you that if these representations are irreducible, then this map only exists if B and W are the same dimension. So then the way you parameterize equivariant functions is by, like, we wanted to parameterize the equivariant functions from this tensor space to itself. So what we do is we take this tensor space, we decompose it in the irreducible representations of our group action, so here. And then once that we have these irreducible representations for the input space and for the output space, then we can match the sub-representations that have the same dimension, and the other ones we cannot match. So that gives us a parametrization of the space of equivariant functions that go from this tensor space to itself, or from this tensor space to a different one. So basically, this is the idea. And then there's some papers that implement this. And so I guess that the hardest part of this algorithm is to take your space and decompose it in these irreducible representations. This is done by something called the Clebsch-Gordon coefficients. And it could be complicated in general, but there's some nice papers that actually implement this for the group SO3, which is the one that is relevant for instance, protein folding. And there's a paper showing that this approach is universal, like approach that people use in these papers, assuming that you can go to arbitrary order of the tensors, right? Because the way you can see this is like these tensors are like if you have a k tensor of a vector v, you can say that's maybe polynomials of degree k on b. And so if the polynomials are dense in your space, then you can universally approximate any function with polynomials. That's the Stone-Weierstrass theorem. But in order to do that, you should be able to use any order of the tensor that you can. Like you need to go to arbitrary high degree polynomials in order for it to be dense. And then the way this is implemented in these papers is by identifying these tensors with spherical harmonics. So you don't have, you can write them as polynomials, and you don't have to use like such a large space in order to represent a k tensor with like k equal to 10 or something like that. And this they can do it because they're working in the sphere. But if you're working it with the different groups, then it could be a little harder to implement. So far so good. I'm gonna move to the next topic. So if you were asleep, then maybe this is a good time to wake up. I just explained how you can use representation theory to represent the equivariant functions with respect to a group action. And so the next thing that I'm going to show is how to use invariant theory. And I hope that from here you can take it that, I mean, it's doable, you use representation theory, but it has some complications, which is like, you still have the issue that you don't know what to do with the nonlinear activation function, and you still have to do this decomposition of the representations in irreducibles, which may be complicated to do. So the next thing that I'm going to show you is how do you use invariant theory. And the idea is basically that one can express the equivariant functions of a space with a given group action if we can understand the invariant theory of that space, or like how the group acts on copies of that space. If we can fully understand the action of the group in that space and where the invariants, then I argue that that allows us to parameterize all the equivariant functions. And I'm going to show you how. So the main idea, the first idea, is to use the first fundamental theorem for invariant theory, which is a classical result that tells you that if you have a function that takes n vectors in Rd and outputs a real number, then this function is OD invariant if and only if you can write it as a function of the scalar products of the input vectors. So maybe I can show you the drawing again. Sorry, I'm going back, but maybe it would have been, sorry. Like this guy, oops, that guy. So you have n particles in Rd, and each particle has a position and velocity. So this is like R, you can think of it as like Rd to the 2n, where n is the number of particles. And then say that you want to predict a function that is invariant, for instance, I don't know, the energy of the system. It's just like to put in context, like what is the thing that I want to say. So I have a function that takes n vectors in Rd and outputs a scalar. This function is OD invariant if and only if I can write it as a function of the scalar products of the input vectors. The proof of this is very simple. So the first thing that we can observe is that if I take a function that you can write as a function of the scalar products, then that function is going to be invariant with respect to rotations, because if I rotate all the vectors here, then these scalar products get like this R transpose R in the middle, and then that cancels out. So this function is obviously invariant. The other question is, how do you know that we can express all the invariant functions in this way? And the answer, one of the answers is like, so for instance, if you have the matrix, this is the matrix of inner products, then you can take this matrix of inner products and reconstruct the original vectors up to OD by doing something like the Cholesky decomposition. And then that would give you all like give you the vectors up to OD. And therefore, since given these inner products, you can reconstruct the vectors up to OD, then every function of these vectors that is invariant can be written as a function of the inner products. And in physics, this is a kind of like a known fact that every scalar function can be written in Einstein summation notation, which is basically just taking inner products and outer products of things. So that's another way to see it. So from here, I ask, okay, I have the invariance. What about the equivariance? So we can use this idea to parameterize all the equivariant vector functions. And the idea is the following. So if you have a function that takes n vectors in Rd, and outputs a vector in Rd, this function is OD equivariant if and only if we can write it as a linear combination of the input vectors so that the coefficients are scalar invariant functions. So basically a functions of the inner products as we saw before. And this works for any dimension, and you don't need to have these irreducible representations in order to parameterize the equivariant functions. For this group action, in particular OD, the idea would be you start with your vector inputs, then you compute your scalars, then you learn these functions f1 through fn, the coefficient functions, f. And then the output is just a linear combination of these coefficient functions times your input vectors. And this architecture is universal, like every function can be expressed in this way. Of course, assuming that your coefficient functions, these functions that you put here, are universal. And so the learning will show up here. This is where the learning happens. So one way to think about this is that we design where the features that give us the parameterization of the equivariant functions. So if we have, like, there's this feature map that takes the inputs and computes the scalars, and we know that any function on these features that you express in this form would be equivariant. So the way I can prove this is like a very intuitive geometric way that works for OD. So basically the idea is that if you have an equivariant function that takes n vectors in Rd and outputs a vector in Rd, then the first thing that you observe is that this function needs to lie, the image of this function needs to lie on the span of the inputs. And the reason is that if it doesn't lie in the span of the inputs, then you can look at a component in the orthogonal complement of the span of the inputs, and then you can find an orthogonal function that fixes that space and moves the other space. Like it moves fixes the span of the input and reverses the component on the orthogonal complement. And so that would give you a contradiction. But that's kind of like the intuitive way to see it. There's also, and then once that you have that, then the rest comes naturally, because you can write the set theoretic kind of definition of this, which tells you like, well, yeah, you can write some coefficients, and this coefficient you can ask them to be invariant by averaging over the orbit. There's also an algebraic way to think about this, and I'm gonna discuss this now. This, by the way, this is something that my postdoc Ben Bloom-Smith, who is amazing, taught me. Like, how do you do this in using like invariant theory, not just like understanding the geometry of the space. And he learned this technique by Gerald Schwartz, and then Gerald Schwartz told him that this is a very old technique that comes back from Malgrange. So the idea is the following. So we have G that acts on B, and we have G that acts on W, and that imposes, or like there's a standard way to define an action of G on the maps from B to W. And so the idea is the following. If G acts on B by phi and G acts on W by psi, then we can define G acting on the maps as G acts on F as the composition of phi, F, and psi, F, and phi inverse of G. So basically, we can see this diagram, and in this diagram, it makes sense. So F goes from here to here, B goes from here to here, and sorry, the action on B is this, the action in W is this, and then we say the action on the map, if F goes from here to here, the action on the map is going back with phi inverse, then going right with F, and then going down with psi. So the action here is the map that makes this diagram commute. And so if you remember, equivariances meant that this diagram commutes, right? That if I go with F and then with the action in the codomain, then I go is the same as apply the action to the input and then apply the function. So basically what I'm saying is that the fixed points on these maps, on the act of the fixed points by the action of G on these maps correspond to the equivariant maps. That's it. So this is kind of, then this justify this curring move that tells you that you can identify the homomorphisms from B to W with the linear maps that go from B tensor product W star, the dual of W, to R. And you can identify that with the when you look at the bilinear maps in B times W star. And so, and if you look at equivariant maps here, you get invariant maps here with the action that I just defined. And this homomorphism that goes from here to here is the thing that would send the map F from B to W to the map that takes V and L to L composed with F of B. And so what this tells us is like, if we can identify, like if we understand the invariance here, then we can identify the equivariance maps here. That's basically the idea. So invariant functions on arbitrary copies of the space can be identified with equivariant functions. That's the move. So, and I'm going to show you how this move works in the example of OD that I told you earlier with this linear combination trick. So this is the proof technique by Malgrange that we learned from Gerald Schwartz. So the idea is the following. Say that we have a function f that takes n elements on a vector space V and output an element of this vector space. And this is an equivariant polynomial. And then we're gonna consider, so this is a function is an equivariant polynomial, and we're going to consider another function that is gonna take n+1 copies of V and it's gonna output a real number. And so these n+1 copies are V1 through Vn, and then the last copy, I'm gonna call it B star to be suggestive that this is maybe an element of the dual. And so the way I'm defining this is saying, okay, this map takes these guys and outputs f of the first n elements, and then it takes the inner product with this B star. So this is a function that evaluates the function f here and then takes the inner product with that. And this is an invariant function. So since this is an invariant polynomial, then since we know what are the invariant polynomials of the action of OD in this space, then we can write it as a function of the inner products. These inner products are the inner products of these guys, the pairwise inner products of these guys, or the inner product of these with any of these guys. So these are my invariant polynomials. And so since we know that this is as a function of V star, this is a polynomial of degree 1, homogeneous polynomial of degree 1, then I can write it as this function is just some polynomial on these guys, I don't know, times just elements of this form, so that what I obtain in the end is a polynomial in B star of degree 1, right? So basically I'm saying, since this function is a polynomial of degree 1 and B star, then only these things need to show up multiplying something of these. This here it could be anything, but here it can just be a degree 1 polynomial. So once that we have that, then we have this expression, and this allows us to cancel out these two guys from this side because this holds for all these stars. So dot product is a non-degenerate form, so we can just cancel this out. And we obtain the formulation that we had in our paper. So basically what we are saying is that understanding the invariance in copies of the space allows you to reconstruct the equivariant functions using algebra. And this suggests an algorithm that basically is what we just did. So we start with the invariant polynomials on B times W star, and then we divide these invariant polynomials in classes. So first are the ones that are degree 0 in W star, then the ones that are degree 1 in W star, and then the rest, which we're not going to use, actually. We just, the only ones that will matter are these ones and that ones, and if there are others that have higher degrees in B star, then are not going to be useful. And once that we have these bases for the invariant polynomials on this space, then we choose a basis for W, E1 to En, and then we choose the dual basis for W, which is the transpose of these guys. Like we are identifying this is like finite dimensions, so we can identify it that way. And then we're going to define these FJs, which is going to be the derivatives of this the invariance of degree 1 with respect to the second coordinate. So it's like, instead of, when I had this expression, instead of just canceling this out, I could have taken the derivative with respect to the second coordinate, and this is what I'm doing here. I take the derivative with respect to the second coordinate, and then I obtain these FJs. And then basically what I say is that the equivariant polynomials are just going to be written as a polynomial combination of like this first invariance, the ones that are degree 0, times the derivatives with respect to the second coordinate of the ones that are degree 1. And that gives me the characterization from invariance to equivariance. And okay, so I have a few examples. I know that it says that I have like many slides left, but actually most of them are after the end, after the references. So after we have that, then we can say, how do we do this for general groups, right? And then from here, we can use that. Actually, now the only thing that we need to do for having a characterization of the equivariant functions for general groups is to understand the invariant functions on copies of the space. And so there's algebra techniques that we can use for that. Basically, the idea is that if the group is reductive, which all the groups that I work on are like very simple objects, like simple Lie groups, and then I don't have any issues with that. Then we know that the algebra of invariant polynomials, we can write it, is something that is called a graded Cohen-Macaulay algebra, which means that you can write it in terms of the primary invariance and the secondary invariance. So basically, every element of this algebra of invariant polynomials can be written as a polynomial of the primary invariance times some secondary invariance. And so the question is, how do we find this primary invariance and the secondary invariance? So in the case of OD, it boils down to actually that the primary invariants were the scalar products and the secondary invariants were trivial. So that made it easier. But this is basically the form that we saw here. The primary, yeah, a function of, we can think of it in that way. Though this decomposition that we obtain in this theorem is unique. Like this tells you that this decomposition that we have here is unique, but the one that we had before may not be unique. But in the case that we care about for machine learning, we actually don't need to be able to have a unique representation. If we have one form of representing, that suffices. Like over-parameterization tells you that there's not a unique solution. So to finish, I'm just going to show a very simple example. Maybe, maybe this example, which says that, okay, so here we have this double pendulum with springs, and we want to predict the dynamics. So what we can do is we can use the fact that this is a O3 equivariant function if we introduce the gravity as one of the input vectors, because if you rotate the system and you rotate the gravity as well, then the dynamics are equivariant with respect to the rotation. Any comment? Okay. So that you can write it that way, and then you can learn it with either a neural ODE, or you can incorporate more symmetries, which you could do by using the fact that the system is Hamiltonian. And so if you do a neural ODE, you basically are learning a differential equation, which is a vector equivariant function. Or if you do a neural ODE, then you just learn a Hamiltonian, which is a scalar invariant function, and you integrate that Hamiltonian using a symplectic integrator. It's just like you are also imposing what is the form of the ODE that this system will satisfy. And the results show that actually the more symmetries that you impose, the better the generalization is. And there's some results, some theoretical results that kind of justify theoretically that claim that I just made. So that's one example. There's another example that has to do with units and vegetation dynamics, which I don't think I'm going to go into because I think I'm already close to the end of my talk, my time. And there's also applications of these to astronomy, and I have some collaborators in astronomy. Basically what they do is they want to predict galaxy properties from dark matter only simulations, and basically they take these dark matter simulations and they construct a set of scalars that represent the objects here, and they do the learning using the scalar features, and yeah, basically that's what they do. And finally, just going to have a summary. Enforcing symmetries in machine learning models is good. It gives you correct model assumptions. It gives you better sample complexity. It gives you small generalization error. It's the right thing to do. Physics book says that you have to do it if you want to do machine learning for physics. And in classical physics, then there's a simple characterization of all equivariant functions with respect to relevant group actions that is based on these scalars that I just showed you. And then we can give you an explicit translation between invariance and equivariance using invariant theory. These are my references for the papers that I mentioned. I mostly focus on this paper. This is the paper where Weichi does these numerical simulations. And this I didn't have time to discuss. And this is the paper that Ben and I are writing about how you go from invariance to equivariance. That will appear in archive soon. Hopefully this talk made sense. Let me know if you have any questions.
Awesome.